Hi, this is Linus, and this is our final project for Class 189, Emotion Recognition from EEG. And our dataset is from OpenNeuro. It is a dataset on emotion with naturalistic stimuli, EEG, and the stimuli is serving us multimedia videos and eliciting the participants' emotions, their reaction to the videos. And our goal is to build an end-to-end EEG classification baseline pipeline, and we parse labels, link stimulus events, and extract this 4-second EEG segments. And we are going to compare using logistic regression and linear SVM on 9 usable subjects. And recent and related work, one of the work that is from the class reading is Allison Opinions. The author talks about the advancement in BCI technology hold potential for developing meaningful clinical intervention for patients with psychiatric and emotion disorders. And the second work is from recent, which is using CNN for emotion and stress recognition using EEG in cognitive therapy sessions. And this research utilized in a CNN network that concentrates on the specific regions of EEG that correspond to emotional arousal, and the researchers implemented and evaluated their architecture using Python to process standard EEG dataset and achieving over 97% accuracy for emotional arousal, and this is a much deeper implementation from our work since it's using a neural network, and so this is going to be have a better accuracy and a much more useful useful work for industry development. And what is our motivation and research question? Our motivation is pretty much emotion recognition from EEG is very meaningful in cognitive science because understanding emotion could benefit people who experiencing emotional disorders with further investigation and medication. And also we are want to do this things is cool for sure. And the research question is, can the machine learning model classify positive versus negative valence from EEG features extracted during emotion eliciting stimuli? And our secondary question is, are simple time domain statistic and bandpower features enough to support a reasonable first baseline, which basically our frequency bandwidths, are we able to extract meaningful and usable data to determine their positive and negative valence. And why we're using binary classification is because we are mainly for just uh, checking if it's a positive or a negative valence from the EEG raw data. So the two-class setup is the easiest and for sure the best setup for us to use. And here's an overview of our dataset. And we have 40 subjects scanned, but there are only 9 subjects usable for our trials, and there are 98 total trials, and which contain 58 negative trials and 40 positive trials for our models to be trained on.
We built an end-to-end EEG emotion classification pipeline using the DENS dataset. Our goal was to classify positive versus negative emotion valence. First, we parsed labels. We use valence as our main binary label because the raw emotion categories field was noisy and inconsistent. We mapped valence greater than or equal to 5 to positive and valence less than 5 to negative. Second, we aligned trials. We matched the stimulus presentation events labeled as STM in the event file with the corresponding rows in the behavior files. Third, we extracted EEG segments for each aligned trial. We chopped it a fixed 4-second window starting from the stimulus onset. Fourth, we built features from those EEG segments. And the last step, we trained it baseline models. One important challenge was that not every subject was usable. We scanned 40 subject folders, but due to missing behavior files and .set and .fdt missing matches, only 9 subjects could be fully processed. This reduced the size of the final usable dataset and directly affected our modeling results. For each trail, we keep 128 EEG channels from E1 to E128. Each EEG segment was 4 seconds long, recorded at 250 Hz, which gave us about 1,001 time points per trial. We used simple and interpretable handcraft features. In the time domain, we extracted the mean and standard deviation. In the frequency domain, we extracted band power for theta from 4 to 8 Hz, alpha from 8 to 13 Hz, and beta from 13 to 30 Hz. This gave us 640 core EEG features per trial, and for baseline models, we trained it logistic regression and linear SVM. We chose those because they are simple, interpretable, and appropriate for first baseline, and for evaluation, we used a standard train test split on the combined all subject feature table. We also saved matrix trained model files and visualization outputs so that the results are reproducible and easier to present. After combining all successful subjects, our final usable dataset contained 9 subjects, 98 trails total, 58 negative trails, and 40 positive trails. For the baseline results, logistic regression achieved 0.56 accuracy and 0.476 F1 score, and linear SVM achieved 0.48 accuracy and 0.381 F1 score. So overall, logistic regression performed better than linear SVM on our dataset. However, those results are still modest, and there are clear reasons for that.
Okay, so for this slide, the main things we want to show is that the logistic regression did a little bit better than linear SVM, but neither model performs especially well on separating this positive class. So looking at the confusion matrices, so we can see that both models are somewhat like better at recognizing negative samples than positive ones. So overall, the results suggest that there is some useful EEG signal in the data, but our current baseline is still limited. This probably because come from the small data set and maybe the variability between the subjects and the fact that we only use relatively simple handcrafted features. So jump to the next pages. That connects directly to our limitation and next steps. One major limitation is that only 9 of the 40 scanned subjects were fully usable. So a lot of the original dataset could not actually make it into the final pipeline. So also 98 trials is still a very small dataset compared to 640 features. Which makes it harder for the model to generalize. On top of that, we only used a simple train test split instead of the stricter subject-aware evaluations. So if we continue this project, the first thing we could do is recover more usable subjects by fixing the file compatibility issues. After that, we would try like reducing the features dimensionally with PCA or regularize feature selections. And we would also like test another EEG features like gamma band power. So finally, we would use cross validation or leave one subject out evaluation to get more reliable estimate. So overall, even though the accuracy is still modest, we and not that good, we think the product is meaningful because we successfully built a full EEG motion classification pipeline and learned a lot about the real challenges of working with EEG data. Logistic regression gave the best baseline result with 0.56 accuracy and 0.476 F1. And this gives us a clear foundation for future improvement. Thank you.